Welcome to the training module on CS546x Power-Meter ICs by Cirrus Logic. This training module introduces Cirrus power measurement ICs and its operations. The industry requirements for electricity metering are evolving rapidly and becoming more challenging for both the meter design companies and the providers of electricity metering equipment. The electric utility and energy consumer wants accurate metering and often across a very wide dynamic range. Compared to traditional mechanical electricity metering devices, the power measurement ICs may specify a measurement range of 1000 to 1. That is, the power flow must be measured accurately with the current input changing over a 1000 to 1 range. The maximum error specifications for the power measurement devices is typically 0.1% of the parameter being measured over the specified dynamic range. To meet the different needs of power measurements, Cirrus developed different ICs with a high degree of commonality and some interesting differences. These ICs combine 2 or 4 delta sigma analog to digital converter channels, followed by a computation engine that performs power calculations and energy to pulse conversion. These ICs are able to accurately measure instantaneous current and voltage whilst calculating instantaneous power, real power, apparent power, IRMS, and VRMS. For the electrical meter market, where reliability and accuracy are key, Cirrus Logic's solution provides the design flexibility to help makers of residential power meters reduce costs and get to market faster with a better quality power meter product. This slide shows 2 data paths. The analog inputs are structured with 2 dedicated channels, voltage and current, then optimized to simplify interface into sensing elements. The voltage sensing elements introduces a voltage waveform on the voltage channel input and is subject to fixed 10 times gain amplifier. Simultaneously, the current sensing element introduces a voltage waveform on the current channel input and is subject to a programmable gain amplifier. Both amplified signals are sampled by delta sigma ADD converters for digitization. The single bit data is passed to the low pass dissemination filter and outputs at a fixed word rate. A digital high pass filter removes any DC components from the selected signal path. After filtering, the instantaneous voltage and current digital codes are subjected to offset or gain adjustments. The digital instantaneous voltage and current data is then processed further. The calibrated energy value is then converted into a pulse output stream with average frequency proportional to a measured energy. These devices perform measurement of instantaneous current and voltage, and from this perform computations of the corresponding instantaneous power, as well as periodic calculations of real energy, RMS current, and RMS voltage. The measurement or calculation results are available in the form of 24-bit signed and unsigned words. All measurements are available as a percentage of full scale. The power measurement ICs provide 3 output pins for energy registration. Each pin's pulse output represents a predetermined quantity of energy based on the different parts and configurations. The quantity of energy represented in one pulse can be varied by adjusting the value in the pulse rate register. Let's look at the pulse output of CS546x. By default, E1 outputs total active energy, E3 total reactive energy, and E2 the sign of both active and reactive energy. Except CS546 and CS546, other CS546x power measurement ICs provide a serial interface for communication between a host microcontroller. If the devices have 5-pin serial interface, they can be connected to a serial EEPROM instead of a host microcontroller. The serial port incorporates a serial port transmit and receive buffer with a command decoder that interprets 1-byte commands as they are received. The serial port can be configured synchronous or unsynchronized communication. Except CS546 and CS546, other CS546x power measurement ICs offer digital DC offset and gain compensation get can be applied to the instantaneous voltage and current measurements, and AC offset compensation to the voltage and current RMS calculations. Since the voltage and current channels have independent offset and gain registers, offset and gain calibration can be performed on any channel independently. During offset calibrations, no line voltage or current should be applied to the meter. A zero voltage differential signal can also be applied to the voltage inputs or current inputs. During gain calibration, a full-scale reference signal must be applied to the meter or optionally scale to the voltage and current inputs. A DC reference must be used for DC gain calibration. Either an AC or DC reference can be used for RMS AC calibrations. If DC is used, the associated high-pass filter must be off. This slide shows the CS546x configured to measure power in a single-phase, two-wire system whilst operating in a single supply configuration. In this diagram, a shunt resistor is used to sense the line current and a voltage divider is used to sense the line voltage. In this type of shunt resistor configuration, the common mode level of the CS546x must be referenced to the line side of the power line. This means that the common mode potential of the CS546x will track the high voltage levels as well as low voltage levels with respect to earth ground. Isolation circuitry is required when an earth ground reference communication interface is connected. A current transformer is connected to the return line current, which implements the tamper detection circuit. This slide shows a single-phase, three-wire system. In many three-wire residential power systems within the United States, only the two line terminals are available. Similarly, it uses voltage dividers to sense the line voltage, but it uses a current transformer to sense the line current. This transformer provides complete isolation from the power lines.